Hello again. Now we're finally going to move on to the math portion of things. So the first topic is we need to learn, or I guess for most of us, just review concentration and how we measure concentration of solutions. If my slideshow will work. Okay, there we go. Molarity is, from what I understand, really the only concentration unit we need to be too concerned about for the AP exam. I know you might have heard of normality or molality in Chem 1, but we're going to focus just on molarity, which is simply the moles of the solute, the moles of the substance being dissolved, divided by the liters of the entire solution, not simply water, not just the water you're adding, but the volume of the whole solution once everything's put together, which can be a little different. So it's just simply a ratio. So just like our molar mass is a ratio of grams to 1 mole that we've been using to do stoichiometry with, molarity is just a new kind of ratio of moles to 1 liter. Yeah, that's really all there's to say about that. So you're going to use molarity in the same way that you use molar mass to do stoichiometry problems. All right, so what happens to the molarity of a solution if more water gets added to it? So like let's say we had a 2 molar solution here. That's how we would say it. If it had a molarity of 2, we would call it a 2 molar solution. Well, what if we doubled the amount of water that we added to it? Well, you can clearly see that it would be half the original concentration. The thing is, when you add more water to it, the amount of moles that are already in there stay the same, but because your volume increases, the molarity is going to decrease. Remember, molarity is moles divided by the volume. So the bigger the volume is, the bigger the number you're going to be dividing into your moles, and that's going to make the answer, the molarity, smaller. All right, so what are molar solutions? A molar solution is one that expresses concentration, usually in moles per liter. And then we also abbreviate it with just a big capital M. It stands for molarity. And then sometimes if you see an ion or a chemical written in brackets and then a number afterwards, well, that indicates the molarity of that ion or chemical. So to make a molar solution, which you're going to do in a lab this week, you're going to need a balance to weigh out the moles of solute, except, as you know, there's no such thing as a molar meter. We have to measure it out in grams and then, of course, convert it to moles. And then you'll need one of these guys. These are called volumetric flasks. I like these. They're not very cheap because they are made very precisely to contain just exactly one particular volume. You can get a 1 liter volumetric flask, you can get a 200 milliliter volumetric flask. We've got a lot of 100 milliliter volumetric flasks. There's only one line on there. This is not like a graduated cylinder or a beaker. There's just one line to the fill line. You take the meniscus to that line, and that's it. And it's made very precisely to do that one thing very well. So we use that to get the liters. So that's, once again, the entire volume of solute and solvent, not just the water. So one way to write the equation is with an N in place of the moles. N means number of moles. And then, of course, the volumes in liters, and that gives you molarity. You can also use the factor label method, or conversion factors is what I call them. Just like we use density as a conversion factor, I like to use molarity as a conversion factor. Sure, you could just plug it into the formula and do algebra, but I think it's quicker and easier to do it with a conversion factor. Now, another one that might pop up on us is mass percent. Mass percent is just sort of like doing the percent yield or doing a percent on an assignment. You just take the mass of the part divided by the mass of the whole. So mass of just your solute divided by the mass of the whole solution times 100 gives you the mass percent. So you could figure out what percentage of the solution was sodium chloride. All right, so it's a ratio of mass, and so it's not very useful in stoichiometry because it's not in moles, but you see concentrations expressed this way sometimes. Like, for example, hydrogen peroxide at the store. It's 3% hydrogen peroxide, which means there's 3 grams of H2O2 for every 100 grams of solution. Alcohols expressed this way. Well, even your milks are 2% and 1%. Now, if you're dealing with really, really tiny concentrations, like if you're measuring the amount of arsenic or lead in the water, obviously that would be hopefully a very small number. You do the same thing, just mass of solute divided by the mass of solution, but you times it by 10 to the 6th. And that gives you the amount of parts of your substance per million. So this is good for small concentrations. All right, so let's do one. Let's calculate the molarity of a potassium chloride solution that has a volume of 400 mils and contains 85 grams of KCl. All right, grams are useless, so first thing we have to do is convert them to moles using the molar mass on the table. Now, I don't round a whole bunch right here because this is not my final answer. To get molarity, which is moles divided by liters, we have to convert our milliliters to liters first. Okay, so the first thing we need to do is take those 400 milliliters and convert them to liters. Milliliters is what we frequently use in the laboratory because it's a, milliliter is a small amount of liquid, but the molarity formula is based on liters. So there's 1,000 milliliters in a liter. So all you're going to end up doing here, and you'll do this in a lot of problems, I don't even show my work for this usually, you're just basically going to end up scooting the decimal place to the left 3. So the number gets quite a bit smaller when you divide by 1,000, just scoot it 3 places over. All right, so now we have our moles of KCl up here, and now we have our liters of solution. Simply plug and chug it in the calculator and then round to 3 sig figs because that's all we had in our least precise measurement, and we get 2.85 molar. So that's how you figure out the concentration of a solution. Now, don't forget to convert to liters, and there's 1,000 mils in a liter. Now, there's another simplifying assumption we can make, and that's utilizing the density of water. Since the density of water is 1, well, a milliliter of water is simply a gram of water. So 1,000 mils of water would be 1,000 grams of water. It would also be a liter. So we're going to assume that our solutions, even though they might have some other stuff dissolved in the water, for the most part, they're mainly water. So we're going to assume that the solution has the same density as if it were pure water. Okay, it's not true, but it's close enough for our purposes. So if we're told a solution weighs 50 grams, we can just assume that that is also going to be 50 milliliters of volume. All right, so making molar solutions from solids. Just going to do a few more examples. How would you prepare 205 milliliters of a 1.2 molar solution? Okay, so in the previous example, we asked what the molarity would be. Now we know what the molarity is, and we just want to know how to make it. How much stuff would we need to dissolve in 205 milliliters? Well, we have two numbers here, the 205 and the 1.2. I'm going to go ahead and say something I hadn't planned on saying until a little later, and that is my tip for figuring out what number to start with here. Okay, this goes back to the difference between intensive and extensive. One depends on how much stuff you have and the other doesn't. Okay, when you start out a conversion factor problem, you need to start out with the number that tells you how much stuff you have. It needs to be a number that depends on the size of the sample. Well, molarity is intensive. It doesn't matter. If you had a bucket of this solution or just 5 drops of it, it would be 1.2 molar. Same goes for, say, water. The density of water is 1. Whether you have a bucket of water or just a test tube full, its density is going to be 1. Those are intensive properties that don't vary with the size of the sample. So, molarity is not going to tell you how much stuff you have. So you don't want to start your conversion factor problems with the molarity. Now, volume and mass, okay, those tell you how much stuff you have. You have 205 milliliters or 0.205 liters. The molarity, milliliters, liters, or grams, any of those tell you how big of a sample size you have. And that's the number you want to use to start out. Okay, now all right, so I'm going to start with the 205 milliliters, convert that to liters, And then now I'm going to use my molarity as a conversion factor. For every 1 liter of solution, I have 1.2 moles of potassium chloride. That's what my molarity tells me. It doesn't tell me that there's 1.2 moles in this much solution. No, it tells us there's that many moles per just 1 liter of solution. And then, remember, we're trying to tell somebody how to prepare this. So giving them moles isn't going to help. We need to convert to grams at this point, using the molar mass, and we'll get 18.3. So to prepare the solution, you would dissolve 18.3 grams of KCl in enough water to make 205 mils. You need to get used to writing it out in a sentence like this and explaining, because 18.3 grams is not going to be the answer. The question said, how would you prepare it? If you asked me that and I just gave you a number, you would be a little frustrated. So you need to go beyond saying just the amount of grams. You need to describe how you would actually prepare it. Dissolve it in enough water to make 205. Not add 205 milliliters of water. No, we want the whole volume of both parts to be 205. So you need to make it clear that you know that. All right, so here's a visual representation of what this would look like. We'd take the 18.3 grams or whatever amount it was, dump it in the volumetric flask, and then fill it just about halfway up the bulb with water, distilled water, of course, and slosh it around, swirl it until it's dissolved, and then dilute it up to volume, to the line, the one and only line on the cylinder, and make sure the bottom of your meniscus touches that line. And so when you're filling these up, be careful so you don't overfill, because as this narrows, it fills up very quickly. And then lastly, if the solution gets warm at all while the material is dissolving, which is quite possible, you'll want to check it again after it's cooled, because the solution will contract as it cools, and then while it was at the meniscus, half hour ago, it may not be any longer. All right, we'll do this one in class, so I'm going to go fast through it. All right, this too I'll do in class with you. It'll only take a second to explain. And this one, I don't know if the dog needs to go out or what, but he's growling at me. All right, now this time we're going to talk about how to make molar solutions from liquids. More accurately, from what we call stock solutions. And that's what you're going to do in the lab as well. You're going to take a stock solution of known concentration and dilute it and do a series of dilutions to make other solutions from your original stock solution. All right, I'm just going to start another video for this since I'm pretty much out of time.